Hidden threads of dark matter stitch the cosmos together. These massive cosmic filaments form a vast web, connecting galaxies across billions of light years. Yet we cannot see them directly. How can something invisible control the motion of entire galaxy clusters and dictate their evolution over billions of years? By the end of this journey, you will understand the invisible architecture that shapes everything we see in the night sky. We will uncover what these cosmic highways are made of and explore the mysterious force that allows them to hold the universe together against its own expansion. What does it mean to live in a universe so deeply interconnected? This cosmic architecture fundamentally reshapes our place in the universe. We are not living in a random collection of isolated islands, but are residents of a specific neighborhood within an immense, structured metropolis. Picture the grandest spider web you can conceive, one whose silken threads are not spun from silk but from the gravitational pull of dark matter. These are the filaments, the foundational scaffolds of the cosmic web. At the points where these threads cross, they form dense nodes, the bustling intersections where galaxy clusters congregate. And between these brilliant strands lie the vast, empty voids, the cosmic deserts spanning hundreds of millions of light years. It is within the filaments themselves that the story of galaxy formation truly unfolds. Vast rivers of primordial gas, the ordinary matter that will eventually form stars and planets, are channeled by this invisible gravitational framework. They flow along these dark matter highways, drawn inexorably toward the intersections. There, the gas pools condenses and ignites, giving birth to the brilliant clusters of galaxies we observe. The scale is almost incomprehensible. A single one of these cosmic threads can be so long that light itself would take hundreds of millions of years to travel from one end to the other. It is this delicate, invisible balance that maintains order, tethering immense structures against the relentless pull of the expanding universe. So what invisible force crafts and sustains this entire web, determining where these threads form and how they endure for billions of years? This invisible mortar is the gravitational force of dark matter, a substance that fundamentally refuses to interact with light. You cannot see it, touch it, or probe it with any telescope ever built. Yet its sheer gravitational presence is what sculpts the entire cosmic web. Imagine trying to build a cathedral using only scaffolding that is completely transparent and intangible. You could see the bricks and the stained glass, but the entire structure would be held aloft by an unseen framework. Dark matter is that framework for the universe. Its gravitational pull creates deep wells of potential, invisible contours in the fabric of space that guide everything else. Ordinary matter, the gas and dust that form stars and planets, simply flows into these pre-existing gravitational channels. Without the immense, concentrated mass of dark matter woven through these filaments, the gravitational grip would be too weak. The universe's relentless expansion would simply tear these structures apart before they could ever form. This makes dark matter the silent, unsung architect of the cosmos. But if dark matter provides the invisible scaffolding, what role does the visible universe, the world we can actually see, play in this grand design? This ordinary matter, the stuff of stars and you and me, begins an epic journey along these invisible roadways. Picture vast rivers of primordial gas and dust flowing into the gravitational valleys carved by dark matter. This is baryonic matter, the protons, neutrons, and electrons that constitute every visible thing in the cosmos. It does not simply sit within the filaments. It travels pulled by the same relentless gravity, streaming toward the dense intersections where galaxy clusters wait. But the journey itself is transformative. As these rivers of gas are funneled into the cosmic threads, they compress, they collide, they heat to incredible temperatures. This is not a calm and smooth flow, but a turbulent, chaotic voyage. Within this chaos, shock waves ripple through the gas, creating pockets of intense density. And in these dense, heated pockets, something miraculous ignites. The first sparks of star formation flare to life, right there within the filament itself. These cosmic pathways become stellar nurseries of an almost unimaginable scale, giving birth to stars and entire galaxies while still in transit. We have even glimpsed this faint, diffuse glow. Telescopes like Hubble have detected the luminous signature of this intergalactic medium, a soft light emanating from the heated gas within the filaments. It is the visible proof of a dynamic partnership, the tangible matter responding to the commands of its invisible guide. So how did we first learn to see these ghostly structures holding the universe together? For decades, these cosmic filaments were only a ghost in the machine. Supercomputers simulating the birth and growth of the universe consistently predicted their existence, painting a picture of a vast, structured web. Yet seeing this architecture in the real cosmos was another matter entirely. The first real breakthrough came not from looking for the filaments themselves, but from mapping everything around them. Projects like the Sloan Digital Sky Survey began a monumental task, cataloging the precise positions of millions of galaxies. When astronomers stepped back to look at this map, the faint outline of the web emerged. The galaxies were not scattered randomly. They traced delicate, interconnected lines like dewdrops on a spiderweb revealing its hidden structure. This was the first indirect evidence, a cosmic footprint of the invisible threads. But how could we prove there was something substantial in the empty spaces between the galaxies? The answer came from some of the universe's most brilliant beacons. Quasars, the intensely luminous cores of distant galaxies, act as cosmic spotlights. As their light travels billions of light years to reach us, it passes through the diffuse gas within these filaments. That gas leaves a distinct fingerprint, absorbing specific wavelengths of light and creating dark lines in the quasar's spectrum. It was like analyzing a distant street lamp through a faint fog, the fog itself revealed only by the light it subtly dims. These absorption lines were the smoking gun, the definitive proof that the filaments were not empty. They were filled with a thin, hot plasma, the very baryonic matter flowing along the dark matter highways. This detective work transformed our understanding. The cosmic web was no longer just a compelling theory from a simulation. It was a tangible, physical feature of our universe, a foundational architecture we had finally learned to see. Mapping this ghostly architecture requires a new kind of cosmic cartography, one that reads the subtle signatures of the unseen. Astronomers now deploy a suite of advanced tools, each designed to catch a different whisper from the dark. Some of the most profound clues come from the very beginning of time, from the cosmic microwave background. This faint afterglow of the Big Bang is the oldest light in the universe, and as it travels across space for billions of years, it is subtly warped. The immense gravitational pull of dark matter filaments acts like a lens, bending this ancient light and creating a minute distortion. Space observatories like the Planck satellite are exquisitely designed to measure these tiny warps, translating them into a map of the invisible mass that caused them. It is like studying the surface of a pond by watching how ripples distort the reflection of the sky. On the ground, massive spectroscopic surveys perform a different kind of census. By capturing the light from millions of galaxies, they can measure their redshift, a key that unlocks not just their distance, but their velocity. This allows scientists to plot galaxies in 3 dimensions, revealing not just where they are, but how they are moving. When you connect these points of motion, the underlying filamentary network emerges in stunning detail, a skeleton traced by the glowing cities it supports. Yet these observations alone are not enough. To truly understand how these threads form and evolve over billions of years, we turn to supercomputers. They create virtual universes modeling the laws of physics on a cosmic scale. Within these digital laboratories, dark matter and gas can be set in motion, their interactions played out over eons in a matter of days. We can watch as gravity sculpts the primordial soup into a familiar web of filaments and nodes, a perfect mirror of the one we see in our telescopes. These simulations are the crucible where theory meets observation, allowing us to test our ideas about the fundamental forces that built our cosmic home. With every technological leap, our maps of this dark web grow more detailed, revealing structures of such immense scale that they challenge our very perception of reality. The sheer scale of these filaments is enough to overwhelm the human mind. Picture a single thread stretching for over 500 million light-years, a distance so vast that light itself takes more than 500 million years to traverse it. Yet its diameter is a comparative thread, only a few million light-years across. If our own Milky Way galaxy were scaled down to the size of a marble, one of these cosmic filaments would be as long as a football field, yet remain as slender and delicate as a single strand of silk. Within this impossibly slender form resides a staggering concentration of mass, often equivalent to thousands of entire galaxies. This is not a solid rope, but a diffuse, flowing river of dark matter and hot gas, a ghostly backbone of unimaginable power. This immense scale dictates the rhythm of cosmic evolution. The gravitational pull of a filament can accelerate entire galaxies, orchestrating dramatic collisions and mergers that trigger furious bursts of star birth. Its very presence can even influence how dark energy, the force driving cosmic expansion, manifests within its domain. Such a colossal structure could not simply appear. Its origins are sewn into the fabric of the early universe, a story written in the faintest whispers of the Big Bang. These ghostly threads were born from the faintest of whispers in the newborn cosmos. In the first moments after the Big Bang, the universe was not perfectly smooth. It was a searing, dense soup of plasma, rippling with tiny variations in density. Some regions were ever so slightly more crowded than others. These minute imperfections, these quantum seeds, were the blueprints for everything to come. Over billions of years, gravity worked as a relentless sculptor. It tugged at those slightly denser patches, pulling matter inward. The first small clumps of dark matter began to form, and through a process known as hierarchical structure formation, they started to merge. It was a cosmic assembly line where smaller structures collided and combined, weaving together to build larger and larger ones. This gravitational weaving ultimately produced the vast filamentary network we see today, a web spun from the tiniest of initial flaws. The stage for this entire epic was set by a phenomenon called cosmic inflation, a brief period of unimaginably rapid expansion that stretched those initial quantum ripples across the entire sky, imprinting them as the fundamental seeds for all cosmic structure. We can still observe the echo of this primordial blueprint. The cosmic microwave background, that ancient afterglow from the universe's infancy, holds a frozen record of those density fluctuations. The subtle hot and cold spots we map in that light are the direct ancestors of the cosmic filaments, the initial conditions from which gravity patiently built an entire universe of interconnected threads. With this ancient origin story in mind, we can now watch these filaments in their mature role, not just as structures, but as dynamic conduits guiding the growth and destiny of galaxies. These cosmic filaments are far more than static architecture. They are the great galactic highways of the universe, conduits of motion and transformation on a scale we can barely comprehend. Entire galaxies are funneled along these gravitational rivers, swept toward the dense, bustling intersections where clusters form. This journey is anything but peaceful. As a galaxy travels, it experiences immense tidal forces, a gravitational stretching and pulling from the surrounding dark matter. This can violently strip away its outer reservoirs of star-forming gas, leaving it a quenched, red, and aging system. Yet in other circumstances, that same compression can trigger the opposite effect, forcing vast clouds of gas to collapse and ignite in brilliant, furious bursts of new star formation. The very identity of a galaxy is forged on this road. A majestic spiral, rich with gas and young blue stars, might be completely remade as it streams into a dense node. Its delicate structure is disrupted through collisions and mergers, its gas exhausted, transforming it into a smooth, featureless elliptical galaxy. This is the primary pathway for galaxy evolution, a journey dictated by the invisible rails of the filament. The flow of matter, however, is not a one-way trip. Cataclysmic events within the galaxies themselves, like supernova explosions or the intense energy blasts from supermassive black holes, can launch enormous winds. These winds drive gas and heavy elements right back out into the intergalactic medium, pushing enriched material back into the filamentary highways. This creates a grand cycle of cosmic recycling, where matter is continuously gathered, transformed, and expelled, only to begin its journey once more. This dynamic feedback loop ensures the filaments themselves are vibrant and ever-changing, not just timeless scaffolds but active participants in the story of cosmic evolution. The entire system is permeated by another layer of mystery, the vast and diffuse dark matter halos that envelop every galaxy and thread through these spaces, their gravitational presence guiding the flow without ever being seen. Every galaxy is cloaked in its own invisible sphere of influence, a dark matter halo. Picture these halos not as isolated islands, but as cities linked by a system of gravitational superhighways. The cosmic filaments are those highways, connecting these vast halos into a single, continuous web. This connectivity allows gravitational forces to travel across truly cosmic distances, orchestrating the motion of galaxies from millions of light-years away. The halo surrounding a galaxy is its anchor, a massive concentration of unseen matter that dictates its rotation and holds its stars in place. Yet the filament is the bridge, a grand conduit that links one anchor to the next, ensuring no galaxy is ever truly alone. Supercomputer simulations reveal a profound relationship between a halo and its address within this cosmic metropolis. A halo residing at a busy intersection, where multiple filaments converge, tends to be older, more massive, and has likely undergone numerous mergers. Its gravitational pull is immense. In contrast, a halo situated along a single filament, away from the crowded nodes, is often still gathering mass, growing steadily as it draws in fresh material from the flowing river of dark matter. This intricate relationship means the very identity of a galaxy, its size, its shape, and its future, is intrinsically tied to its location within the grand cosmic web. To see this principle in action, we can look toward the most densely populated urban centers of the universe, the great galaxy clusters. The Coma cluster stands as a celestial metropolis, a dense swarm of over 1,000 galaxies some 300 million light-years away. Here, the abstract concept of the cosmic web becomes breathtakingly real. Faint, luminous threads stretch out from the cluster's core like umbilical cords, reaching deep into the surrounding cosmic voids. These are the filaments in action, actively channeling fresh galaxies and vast rivers of hot gas into the cluster's waiting gravitational embrace. We can detect these ghostly structures through two remarkable methods. The first is the faint X-ray glow emitted by the incredibly hot gas, millions of degrees in temperature, that is flowing along the filament. The second is through gravitational lensing, where the immense but invisible mass of the filament warps the very fabric of space, bending the light from galaxies far behind it and revealing its presence like a fingerprint. This is not a static sculpture. The filaments are actively shaping the cluster's internal life. Studies show that the direction and speed of galaxies orbiting within the Coma cluster are deeply influenced by the gravitational pull of these incoming threads. It is as if the highways leading into a great city are dictating the flow of traffic within its very center. This real-world observation confirms that filaments are not merely passive scaffolding. They are dynamic supply lines, continuously feeding the growth of the largest structures in the universe and governing the motion of everything within them. As we watch this ongoing cosmic construction, a deeper question emerges. How do these delicate threads, which so clearly bind the universe together, withstand the relentless force that is trying to tear it all apart? At the heart of the cosmos, a grand and silent conflict unfolds. On one side is dark energy, the mysterious force driving the universe to expand at an ever-increasing rate, pushing galaxies apart. On the other side is the immense gravitational pull of the cosmic filaments, the invisible threads that work to hold everything together. These filaments create localized pockets of stability, where their gravity is strong enough to counteract the universe's outward rush. Within these anchored regions, galaxy groups and clusters remain bound, their structures preserved against the cosmic tide. Venture further out, however, into the emptiness far from any filament, and the story changes completely. There, with no significant gravitational anchor to resist it, dark energy reigns supreme. Expansion proceeds unimpeded, causing the vast cosmic voids to grow ever larger and emptier over billions of years. This delicate tug of war between the global push of dark energy and the local pull of filamentary gravity is what sculpts the evolving architecture of the cosmic web. It determines which galaxy groups will remain gravitationally linked for eons and which will be irrevocably torn asunder, their constituent stars isolated in the growing darkness. This balance is not just a matter of cosmic geography, it is the key to understanding the ultimate fate of everything we see. As we observe this struggle, we are forced to confront the limits of our knowledge, peering into a future where the very nature of space and time remains the greatest mystery of all. Gravity may be the master architect of the cosmic web, but it does not work alone. An unseen partner operates within these vast filaments, a force generated by the motion of the universe itself. This is the influence of magnetic fields. As rivers of ionized gas flow along the gravitational highways, their charged particles create immense, invisible magnetic fields that weave through the cosmic threads. These fields are incredibly subtle, their strength a tiny fraction of Earth's own magnetic field, yet they stretch across millions of light years. Their effect is not to build the structure, but to guide the traffic within it. One of their most fascinating roles is aligning galaxies. As galaxies form and travel within a filament, their spin axes can become oriented by these vast magnetic fields, like countless compass needles all pointing along the same invisible line. This creates a strange kind of cosmic order, a coordinated dance choreographed by forces we are only beginning to understand. These magnetic fields also act as conduits for cosmic rays, the high-energy particles that race across the universe. The fields channel these rays, funneling them along the filaments and preventing them from scattering randomly into the empty voids. In some filaments, magnetic pressure may even help to confine the incredibly hot gas, acting as an invisible barrier that keeps this vital star-forming material from simply drifting away into the cosmic emptiness. We have direct evidence of this magnetic activity. Radio telescopes have detected a faint signal known as synchrotron radiation emanating from within some filaments. This specific type of light is the unmistakable signature of electrons spiraling at near light speed around magnetic field lines. It is a ghostly glow that confirms these structures are not just gravitational but magnetized. While their power is secondary to the overwhelming pull of gravity, these magnetic fields add a crucial layer of complexity to the cosmic web. They remind us that the universe is not built by a single force, but through the intricate interplay of many. Capturing this delicate interplay in a computer model, however, pushes the very limits of our technology. Building a virtual universe is a task of almost unimaginable complexity. The most powerful supercomputers on Earth dedicate millions of processing hours to simulating the growth of the cosmic web, and even then, they face profound challenges. Models like the illustrious TNG simulation are monumental achievements, yet they still struggle to replicate the delicate, thread-like nature of real filaments with perfect accuracy. The primary obstacle is resolution. To simulate the entire observable universe, you must divide it into a digital grid, and the size of each grid cell sets a fundamental limit on the detail you can capture. It is like trying to paint the fine silk of a spiderweb with a paintbrush that is simply too thick. Within these simulations, the behavior of ordinary matter, the baryonic gas, is notoriously difficult to model. This is not a smooth, placid fluid. It is a turbulent, superheated plasma churned by shock waves, stirred by magnetic fields, and constantly being recycled by stellar winds and supernova explosions. These feedback processes inject vast amounts of energy back into the system, disrupting the gas flow in ways that are incredibly difficult to predict and encode into an algorithm. The result is that simulated filaments often appear thicker and more diffuse than the delicate structures we infer from our telescopes. Their predicted density of hot gas might not quite match the faint X-ray glow or the subtle absorption lines we detect in the real cosmos. Yet these very discrepancies are not failures, they are invaluable guides. They highlight the gaps in our understanding, pointing directly to the physical processes we have not yet mastered. Each shortcoming in the simulation forces us to ask deeper questions, pushing our observational techniques and theoretical models to new heights. This ongoing dialogue between the virtual and the real universe is a cornerstone of modern cosmology. It is a process of continuous refinement, where every challenge overcome reveals a new layer of cosmic truth. And one of the most pressing questions these simulations raise concerns the state of the matter flowing through these cosmic channels, prompting a direct investigation into its temperature and energy. The search for this elusive gas has its own name, the warm-hot intergalactic medium. It is a ghost in the machine of the cosmos, a plasma so hot it glows only in the faintest X-rays, yet so diffuse that it barely registers at all. This is not the calm, cool hydrogen of deep space. This material has been superheated by its own turbulent journey, shocked and compressed as it flows into the gravitational valleys of the dark matter filaments. The temperatures here are staggering, ranging from 100,000 to 10 million degrees Kelvin. At such extremes, atoms are torn apart into a soup of charged particles, a state that makes them incredibly difficult to see. They are too hot to absorb light in a clear, simple way, yet too spread out to emit a strong, detectable glow of their own. For decades, this presented a fundamental problem. How do you find something that is effectively invisible? The answer required looking not for the gas itself, but for its subtle interaction with the universe's brightest lights. Astronomers turn their most powerful eyes, ultraviolet and X-ray telescopes, toward distant quasars. These brilliant beacons act as cosmic backlights. As their intense radiation travels for billions of years to reach us, it passes through these filaments. The warm, hot intergalactic medium within the threads leaves a faint fingerprint, absorbing specific, telltale wavelengths of the quasar's light. It is like detecting a specific kind of fog by the precise colors it removes from a distant spotlight. Each successful detection is a hard-won victory, a single day to point on a map of the invisible. Why is this difficult hunt so crucial? It holds the key to solving one of astronomy's most persistent puzzles, the missing baryon problem. For years, our census of the universe's ordinary matter, the protons and neutrons that make up stars, planets, and us, did not add up. A significant portion of this expected material was simply unaccounted for in our surveys of galaxies and gas clouds. The warm-hot intergalactic medium is that missing component. This diffuse, hot plasma woven through the cosmic filaments represents a vast reservoir, potentially containing up to half of all the ordinary matter in the entire universe. Every filament we map is another chapter in this story of cosmic accounting, revealing where the building blocks of reality have been hiding all along. This discovery reshapes our understanding of galaxy formation itself. The warm-hot intergalactic medium is not just a passive component, it is the primary fuel reserve for future cosmic cities. This superheated gas is the raw material from which new galaxies will eventually condense, and it is the reservoir that existing galaxies draw upon to continue forming stars. By tracing its distribution, we are essentially mapping the future potential for star birth across the cosmos. The Great Cosmic Web is not merely a structure of the present, but a dynamic system where the fate of matter is continually decided. Its journey from a diffuse, invisible haze to the brilliant light of a star, all guided by the pull of an unseen hand. This generative flow of gas is the lifeblood of the cosmos, a continuous delivery system that ignites star formation on a colossal scale. When a massive river of pristine hydrogen and helium, channeled by a dark matter filament, pours into a region where a young galaxy is taking shape, the effect is immediate and dramatic. The sudden influx of fuel creates immense pressure, forcing vast clouds of gas to collapse under their own weight. This triggers what astronomers call a starburst, a ferocious period where star formation erupts at a rate hundreds of times faster than in our own tranquil Milky Way. These cosmic fireworks were especially common in the early universe, when the Filamentary network was first establishing its vital supply lines to the burgeoning galactic neighborhoods. But the influence of these threads extends far beyond simply delivering raw materials. The very structure of a galaxy can be molded by its journey along a filament. As a galaxy moves within this gravitational river, it experiences powerful tidal forces, a subtle stretching and pulling from the surrounding dark matter. This gravitational stress can be enough to stir a galaxy's internal structure, encouraging the formation of a central bar or amplifying the graceful sweep of its spiral arms. The grand design of a majestic spiral galaxy may, in part, be a signature of its long passage along a cosmic filament. This constant replenishment of gas is what allows galaxies to maintain their vibrant stellar nurseries for billions of years. Without this steady stream from the cosmic web, a galaxy would quickly burn through its initial fuel reserves. Its star-forming factories would shut down, and it would fade into a quiet, red, and aging system. The filament is not just a road, it is a dynamic and creative force, actively shaping the destiny of every galaxy that travels its length. This intimate connection between a galaxy and its filamentary highway inevitably sets the stage for the next great cosmic drama, where these same pathways bring entire worlds into a fateful collision course. The same filaments that deliver the raw materials for star formation also orchestrate the most dramatic encounters in the universe. As galaxies stream along these cosmic highways, their paths frequently intersect, bringing them into a gravitational dance that can reshape their very essence. These are not simple near misses, but deep, transformative interactions. The immense pull of a passing galaxy can stretch a neighbor into long, streaming tails of stars and gas, violently stripping away its outer layers and quenching its ability to form new stars. In other, more cataclysmic meetings, two galaxies can be drawn into a direct merger, their structures completely disrupted as they spiral together over hundreds of millions of years. This chaos, however, is profoundly creative. The immense gravitational forces at play during a merger can funnel vast reservoirs of gas directly into the central supermassive black holes of the colliding galaxies. As this gas spirals inward, it heats to incredible temperatures, igniting the most luminous objects in the cosmos, quasars. These brilliant beacons can outshine their entire host galaxy, a direct result of a galactic collision orchestrated by the filament that brought them together. A perfect example of this cosmic construction unfolds in the Antennae Galaxies, a famous pair currently entangled. Their long, streaming tails, which give them their name, were drawn out by tidal forces as they were pulled together along a shared filamentary structure. Within their colliding hearts, millions of new stars are bursting to life in brilliant blue clusters, while their central black holes are likely feasting on the delivered gas. These violent events serve a crucial purpose for the wider cosmos. They act as giant blenders, redistributing a galaxy's angular momentum and, most importantly, scattering newly forged heavy elements far into space. Supernova explosions triggered by the merger launch oxygen, carbon, and iron out into the filamentary channel, enriching the intergalactic medium with the very building blocks for future planets and life. This is why filaments are such vibrant hubs of cosmic activity. The density of galaxies moving along these shared paths makes interactions and mergers far more frequent here than in the isolated emptiness of the cosmic voids. Every close encounter, every dramatic collision, is a testament to the filament's role as both a creator and a destroyer, continuously forging new galactic forms from the wreckage of the old. Such relentless dynamism, however, forces us to wonder how these delicate threads can possibly maintain their coherence over billions of years. These cosmic threads are survivors on an epic scale, enduring for billions of years while the universe itself tears at their seams. Their remarkable longevity is a direct result of the dark matter that forms their core. Dark matter's gravitational pull creates a deep, stable foundation, an anchor that resists the relentless outward push of cosmic expansion. Imagine a vast, invisible net submerged in a rushing river. The water strains to carry it away, but the net's own weight and structure hold it firmly in place. The cosmic web functions in a similar way, with dark matter providing the gravitational weight that keeps the entire structure coherent. Over immense timescales, these filaments are not static. They can grow thicker and more massive as they siphon dark matter and gas from the surrounding voids, a slow and steady process of cosmic accumulation. Yet they also face a constant opposing force. Dark energy works to stretch the space between the nodes, pulling the filaments taut and potentially thinning their internal density. This creates a slow-motion evolutionary dance, a balance between growth and attrition that plays out over eons. Supercomputer models reveal a fascinating detail within this grand stability. While the filament itself persists as a coherent structure, the galaxies within it are like individual cars on a highway, able to enter, travel along, and eventually exit. The road remains even as the traffic changes. This enduring network provides a unique historical record. By studying the age, thickness, and density of filaments in different parts of the universe, astronomers can read the history of cosmic structure formation. They can trace how the web has strengthened and evolved from the early universe to the present day. This long-term perspective reveals the filaments as more than just a feature of the cosmos. They are its enduring skeleton, shaping and being shaped by the flow of time itself. And this persistent framework has played a crucial role in distributing the very elements that make life possible. These cosmic filaments serve as the great distribution network for the elements of life itself. When a massive star reaches the end of its life and explodes in a supernova, it forges heavy elements in its final, violent moments, scattering oxygen, carbon, and iron into the surrounding space. This enriched material does not simply linger in one place. It is swept up by the gravitational currents of the filament, entering a vast, flowing river that carries these vital ingredients across millions of light years. This process is a form of cosmic recycling on a grand scale, where the ashes of dead stars become the building blocks for new worlds in entirely different galactic neighborhoods. We have direct observational proof of this distribution at work. By studying the light from distant quasars as it passes through these filaments, astronomers detect the distinct absorption signatures of these heavy elements. It is like finding the chemical fingerprint of a supernova in the most remote and seemingly empty corridors of space, a clear sign that the filaments are actively transporting this enriched material. Without this intricate web, the universe would be a patchwork of chemical deserts and oases. Galaxies forming in isolated regions might be starved of these heavier elements, potentially lacking the raw materials to form rocky planets or the complex chemistry that underpins life. The filamentary network ensures a more uniform mixing, seeding even the most remote proto-galaxies with the same elemental diversity found in our own cosmic backyard. This constant circulation ties into a larger dynamic, the great flows of matter that the filaments orchestrate across the entire visible universe. Our entire galactic neighborhood is caught in a vast and silent river. The Milky Way, along with thousands of other galaxies, is not drifting aimlessly, but is being pulled by immense, coherent flows that course along the cosmic filaments. These are not gentle currents, but powerful rivers of motion where entire galaxies can be swept along at hundreds of kilometers every second. Their direction is not random. It is a direct response to the gravitational landscape, a flow from the cosmic highlands of empty voids down into the deep gravitational valleys carved by the densest clusters. This universal choreography allows us to perform a remarkable kind of celestial cartography. By meticulously tracking the peculiar velocities of galaxies, their deviations from the general expansion of space, astronomers can essentially trace the gravitational field of the unseen universe. These motions become a proxy for mapping the dark matter itself, revealing the true mass of the structures doing the pulling, a mass that often far exceeds what the visible light of their galaxies would suggest. The ultimate destination for our own local flow is one of the great cosmic mysteries, a region of such immense gravitational pull it is known as the Great Attractor. It lies hidden behind the dense plane of our own Milky Way, its true nature obscured by intervening stars and dust. We know it is there because of our motion, a relentless trajectory that pulls our entire local group of galaxies toward a point in the constellation Centaurus. This journey, guided by the filamentary highway we are on, underscores a profound truth. The cosmos is in a state of constant, directed motion, a grand migration on a scale that defies human comprehension. These great flows converge at specific, bustling intersections, the nodes where the cosmic web's threads are woven most tightly together. At the bustling intersections of these cosmic highways, the nodes form the universe's grandest cities. Here, multiple filaments converge, weaving their gravitational influence into a single, deep well where matter and galaxies pool from every direction. It is a place of immense density and relentless activity, the polar opposite of the quiet, empty voids that separate these brilliant hubs. The Virgo cluster offers a stunning nearby example, a sprawling metropolis of over 1,000 galaxies residing at a node where several major filaments meet. This convergence makes it a crucible of cosmic evolution, where galaxies are constantly arriving, interacting, and being transformed. Within these nodes, the sheer concentration of mass creates an environment of extreme physics. The space between the galaxies is not empty, but filled with a superheated plasma known as the intracluster medium. This gas is so incredibly hot, reaching temperatures of tens of millions of degrees, that it glows not in visible light, but in a fierce, diffuse X-ray halo that envelops the entire cluster. This X-ray emission is a direct signature of the node's intense gravitational squeeze, a testament to the vast amounts of energy being released as matter falls into this deep potential well. The nodes are also where dark matter reveals its presence most clearly. The combined mass of thousands of galaxies, along with this searing intracluster gas, still does not account for the total gravitational pull we observe. The majority of the mass holding the cluster together is the invisible dark matter, whose distribution can be mapped by watching how its gravity warps the light from more distant galaxies, a phenomenon called gravitational lensing. These lensing maps show the dark matter concentrated in a smooth, massive halo that permeates the entire node, the true gravitational anchor of the cosmic city. This hierarchy of structure, from the slender filaments to the dense, brilliant nodes and out to the vast, empty voids, forms the complete anatomy of our universe. Understanding the nodes is to understand the ultimate destinations of the cosmic web's great flows, the places where gravity's long work finally culminates in the most spectacular gatherings of matter in the cosmos. Between these brilliant threads of the cosmic web lie the great cosmic voids, unimaginably vast regions of near emptiness. These are not simply blank spots on the map, but active, expanding domains that define the negative space of the universe itself. While filaments and nodes contain most of the cosmos's matter, the voids claim most of its volume, immense bubbles of nothingness that can span hundreds of millions of light years. They are the ultimate deserts where the density of galaxies is a tiny fraction of what we find in the bustling filaments, yet to call them completely empty would be a mistake. Scattered across these barren expanses are isolated galaxies, often strange and misshapen wanderers that evolved in profound isolation, untouched by the galactic collisions that shape their cousins in the dense web. A faint, diffuse mist of hydrogen gas also permeates the void, but it is so thin that its presence is incredibly difficult to detect. Here, far from the gravitational anchor of a major filament, the influence of dark energy is supreme. The expansion of the universe is most potent within these voids, causing them to grow larger and emptier with each passing eon. This relentless growth stretches the very fabric of the cosmic web, pulling the filaments tauter and influencing how they evolve. In a strange twist of physics, the overwhelming lack of matter in a void creates a unique gravitational phenomenon. While gravity is always attractive, a region of such profound emptiness acts like a slight hill on the cosmic landscape. Matter from the denser surrounding filaments naturally flows away from this hill, down into the deeper gravitational valleys of the web. This gives voids a kind of repulsive effect, gently pushing galaxies and gas toward the filaments and nodes, further sharpening the contrast between the web's dense structures and its empty spaces. Studying these great voids is just as crucial as mapping the brilliant filaments. They provide the essential counterpoint, the silent background against which the cosmic web's intricate architecture is drawn. This dramatic duality between the densely woven threads and the expansive emptiness highlights a universe of incredible structural diversity. It forces us to ask why matter clumped in such a specific, web-like pattern, and what delicate balance of forces in the early cosmos made this stunning contrast possible. The specific cosmic web we observe was not a guaranteed outcome. Its existence hinges on a deeply precise calibration of the universe's initial settings. The exact strength of those primordial density ripples, the ratio of invisible dark matter to the mysterious push of dark energy, all of these values had to fall within an extraordinarily narrow range for filaments to ever form. If the initial fluctuations had been just a bit stronger, gravity would have pulled matter together far too aggressively, causing the entire cosmos to collapse into a giant black hole long before galaxies could ever take shape. Conversely, if those ripples had been slightly weaker, the gravitational tug would have been insufficient. Matter would have remained a diffuse, featureless haze, forever unable to condense into the magnificent threads and nodes we see today. This delicate balancing act extends to the cosmic ingredients themselves. Too much dark matter, and the universe would have folded in on itself eons ago. Too much dark energy, and the expansion would have been so violent that it would have ripped apart every incipient structure before it could even begin to coalesce. This realization that our universe seems perfectly tailored for complexity naturally leads to a profound question. Why does our cosmos possess this seemingly perfect recipe for a web of life-giving structures? One compelling possibility explored by cosmologists is the multiverse. This idea suggests our universe may be just one of countless others, each with its own unique set of physical constants and initial conditions. In most of these other universes, the parameters might be all wrong for web formation, resulting in sterile, empty expanses or short-lived, collapsed realities. We simply exist in one of the rare, fortunate versions where the numbers align to allow for galaxies, stars, planets, and ultimately, observers. While the laws of physics naturally give rise to structure, the specific, intricate web we call home reflects a 1 in a trillion cosmic lottery ticket. This reflection on our universe's unique recipe pushes our observational tools to their absolute limits, guiding the next generation of telescopes designed to map the earliest strands of this cosmic architecture. The next generation of cosmic cartography is already taking shape. New observatories are poised to peer deeper into the cosmic web than ever before, transforming our grainy maps into high-definition portraits of this hidden architecture. The James Webb Space Telescope will act as a powerful infrared eye, capable of detecting the faintest starlight from the earliest galaxies, revealing how they aligned and formed along the very first filaments. Meanwhile, the European Space Agency's Euclid mission is designed for a singular, grand purpose: to create the most extensive three-dimensional map of the universe. It will chart the positions and shapes of billions of galaxies, tracing the dark matter scaffolding between them with breathtaking precision through the subtle distortions of gravitational lensing. On the ground, the future square-kilometer array radio telescope will listen to the whispers of neutral hydrogen gas, mapping its distribution across cosmic time and directly imaging the vast, flowing rivers of fuel within the filaments themselves. Together, these instruments will hunt for the elusive warm-hot intergalactic medium, not just in absorption, but in its own faint emission, finally allowing us to see the glowing veins of the cosmic web directly. The data they gather will resolve long-standing puzzles, pinpointing the exact temperature and density of this missing matter, and detailing how filaments have thickened and evolved over the last 10 billion years. Even gravitational wave astronomy will contribute to this new vision. Future space-based observatories will detect the ripples in spacetime from countless colliding black holes and neutron stars. By analyzing the rate and distribution of these cosmic mergers across the sky, scientists can infer the underlying large-scale structure that guided them, reading the history of galactic collisions written by the Filamentary web. This incoming flood of data will not merely add details to our existing models. It will force us to rewrite the story of cosmic evolution. It will challenge our simulations, reveal new physical processes, and perhaps uncover entirely unexpected phenomena occurring within these dark matter channels. As we stand on the brink of this observational revolution, we are compelled to reflect on what this intricate, interconnected universe ultimately means for our own place within it. This cosmic architecture does more than map the universe. It maps a fundamental shift in our own understanding. To learn that our galaxy is woven into a vast web by invisible threads is to feel both incredibly small and profoundly connected. We are not just observers looking out at a distant cosmic stage. We are participants embedded within a dynamic, living structure. This realization touches a deep human curiosity, a drive to find pattern and meaning in the grand tapestry of existence. Philosophers throughout history have sought a unifying principle in nature, and here it is, written across the sky in gravitational ink. The elegant order of the cosmic web, with its balance of dense nodes and empty voids, speaks to a universe governed by laws that are both beautiful and comprehensible. Contemplating the sheer scale of these filaments inevitably brings a sense of humility. Our entire world, with all its history and complexity, exists within a single neighborhood of a single thread in an immeasurable web. Yet this perspective is not meant to diminish our significance, but to expand our sense of belonging. We are made of stardust that was itself forged in galaxies and distributed along these very cosmic highways. The same forces that gently pull our Milky Way toward the great Attractor also govern the orbits of planets and the falling of rain. This interconnectedness is a source of boundless inspiration, fueling our desire to build ever better telescopes and to ask ever deeper questions. The scientific pursuit to chart the dark web and the philosophical wonder it evokes are two sides of the same coin, both driven by the awe of discovering our true context within an interconnected cosmos. We have traced the story of the cosmic web from its faint origins to its present-day grandeur. These massive threads, woven from dark matter and channeling rivers of hot gas, are the gravitational scaffolding that binds the universe into a coherent whole. They dictate the birth and evolution of galaxies, distribute the very elements for life, and stand as a testament to the delicate balance between the universe's expansion and its gravitational heart. Our journey has taken us from supercomputer simulations to the faint glow of the warm, hot intergalactic medium, from the quiet stability of dark matter halos to the violent, creative chaos of galactic collisions. With every new telescope and every deeper map, we refine our understanding of this fundamental architecture. The awe this inspires is not just scientific, it is deeply human. It connects us to a cosmos far grander than our daily lives, a universe where invisible forces craft beauty on a scale beyond comprehension. The next time you gaze up at the stars, remember you are not looking at scattered, isolated points of light. You are seeing the glittering nodes of a vast, interconnected web, a single neighborhood within an immense cosmic metropolis held together by threads of gravity. We would love to hear what fascinates you most about these cosmic structures. Share your thoughts in the comments and join us as we continue to explore the profound mysteries of space.